Very good morning, all of you. Myself Chetna, roll number 2362, and today my presentation topic is Uniform Convergence and Uniqueness Theorem. So, firstly, let's define what we mean by uniform convergence. A sequence of function is said to be uniformly convergent on the interval, which is the domain of the sequence, closed interval AB, to a function f to which it converges. And the condition is if for any epsilon which is positive and for all x in the domain AB there exists an integer which depends only on epsilon and independent of x, such that modulus of fnx minus fx is less than epsilon for all n greater than capital N. This is the definition of uniform convergence. So let's consider an example. We have given a sequence fnx which is equals to 1 upon n plus x, and we have to show that this sequence is uniformly convergent on the domain 0 to b, where b is any positive number. So the solution is, as we have defined in the definition of uniform convergence, we will consider modulus of f and x minus f of x. So here f of x is equals to limit n tends to infinity f and x, which is equals to limit n tending to infinity 1 upon n plus x, and which comes out equals to 0 for all x which belongs to the domain 0 to b. Thus the sequence converges pointwise to 0. पॉइंट वाइज मीन्स हर एक्स के लिए वो कन्वर्ज कर रही है ज़ीरो को. सो द कन्वर्जेंस इज पॉइंट वाइज. For the uniform convergence, we will consider modulus fnx minus fx must be less than epsilon. This implies mod of 1 upon n plus x minus 0 less than epsilon, because f of x comes out 0. That is 1 upon n plus x modulus is less than epsilon. Or from this inequality we can obtain inequality in terms of n, that is n is greater than 1 upon epsilon minus x. Now if n is greater than 1 upon epsilon minus x, since we have considered epsilon as very small, near about to 0, so 1 upon epsilon is becomes a large integer, large number, and x is subtracted from that number. So as x increases, the value of n decreases, and as x, so we can say that n which is greater than 1 upon epsilon minus x, which will decrease with x, and the maximum value will be when x is equals to 0, which comes out to be 1 upon epsilon. Thus we can choose an integer n which is equals to or just greater than 1 upon epsilon, and then if small n is greater than that n, then modulus of fnx minus fx will be less than epsilon. So which is the required condition for the uniform convergence of any sequence. So we can obtain that particular n which is finite. So we can say that the sequence is uniformly convergent on the domain 0 to b, where b is any positive number. Now let's consider Cosi criteria for uniform convergence of sequence of functions. The statement is a sequence of real functions which are defined on the set x converges uniformly on x. Means here the domain, complete domain is considered, and the condition is for every epsilon greater than 0 there exists n naught which belongs to n natural numbers, and depending only on epsilon independent of x or independent of the members of the domain. And the condition is such that modulus of fnx minus fmx is less than epsilon for nm greater than n naught and x belongs to capital X or the domain. Right, we can say that the difference of two terms after a fixed term becomes less than epsilon, then the sequence f and x will be uniformly convergent. Or in the parallel form we can write the expression in modulus fn plus mx minus fnx less than epsilon for n greater than n naught and m belongs to natural numbers. So let's move to the proof. Suppose that fnx is uniformly convergent to f on the domain x. So by the definition of uniform convergent, modulus of fnx minus fx will be less than epsilon by 2 for n greater than n naught and x belongs to the domain x. Let n and m be any two numbers, two integers which are greater than n naught and x belongs to the domain x, then modulus of fnx minus fmx will be less than equals to modulus of adding and subtracting fx in the left hand side, then and applying the triangle inequality, then we get modulus of fnx minus fmx will be less than modulus of fnx minus f of x plus modulus of fmx minus f of x, and we both are less than epsilon by 2, so the modulus fnx minus fmx will be less than epsilon. So which is the condition for the uniform convergence. So conversely we will consider that the given condition holds, therefore fnx will be a Cosi sequence in R for each x in the domain x, and we know that set of real numbers is complete. It follows that fnx converges to some value f of x for each x in the domain. Hence fnx converges to fx pointwise. So because of the completeness of R, the pointwise convergence is fixed or is assured, and we need only to show the convergence is uniform. And to show that let epsilon greater than 0 be given, then by the hypothesis there exists n naught which depends only on epsilon, such that mod fnx minus fmx less than epsilon for nm greater than n naught x below, which is the given condition in the statement of the theorem. And now if we fix n and let m tends to infinity, then what we get? Modulus of fnx minus limit and m tending to infinity fmx, which is fx. So replacing fmx by fx, we get fnx minus f of x less than epsilon for all n greater than n naught and m tends to infinity. So we'll not define here m, will not consider m that m is greater than particular n naught. We have tends m towards the infinity. So this is the required condition for the uniform convergence. So the proof complete. Now M test for the uniform convergence of sequence of functions. Here the statement is let fnx be a sequence of functions such that limit n tending to infinity fnx is equals to f of x for all x in the domain AB. Here we have given a sequence fnx and the limit of that sequence is equals to f of x for all x, means the convergence considered here is the pointwise. And again we consider mn, which is equals to supremum of fnx minus f of x over the domain AB close interval. Then it says that the sequence fn will converge to f uniformly if and only if that mn, which is supremum of fnx minus fx, tends to 0 as n tends to infinity. So let's move towards the proof, and the necessary condition is let the fnx tends to fx uniformly for all x in the domain AB, then mn which is defined in the statement, mn which is equals to supremum of fnx minus f of x. Since fn converges to f uniformly, so modulus of fnx minus fx will tend to 0, so their supremum will also be less than epsilon over all x in the domain AB, and this implies that this supremum will tend to 0 because of the uniform convergence as n tends to infinity. And the sufficient condition, let mn tends to 0 as n tends to infinity, such that for epsilon greater than 0 there exists such integer that mn minus 0 is less than epsilon for all n. This is clear. This inequality is clear as mn tends to 0, as n tends to infinity. So mn minus 0 modulus will be less than epsilon for all n greater than or equals to n. Or we can see mn as a sequence of real numbers and which converges to 0. Or we can say that modulus of mn less than epsilon for all n greater than or equals to n. That is mn which is equals to supremum of modulus fnx minus f of x will be less than epsilon. This implies modulus of fnx minus f of x will be less than epsilon for all x. Means if it is less than epsilon, its supremum is less than epsilon, then that quantity for all x will also be less than epsilon, and which is the required condition for the uniform convergence of any sequence on the domain AB. This completes the proof of M test for the uniform convergence of a sequence of function. Both the necessary and sufficient conditions are proved here. Now let's consider the uniqueness theorem for the power series. Here the statement is, if an xn and bn xn converges on some interval minus r to r. Here r is the radius of convergence, or we can say interval of convergence, and r is positive. To same function, if both the power series converges to the same function f, then each term of the power series are equal. Since in the definition we have considered that both the series converges, so because of this convergence, the function f to which both the series converge has derivatives of all order in the domain of convergence or interval of convergence, and the mth derivative of f are given by differentiating both the sequences m times, which is simply the derivative of x raised to power n. So differentiating m times, we get summation n running from m to infinity, n into n minus 1, n minus 2, up to n minus m plus 1 an x raised to power n minus m. Now putting x is equals to 0, this gives f mth derivative of f at 0 is equals to m factorial am when x is equals to 0, and similarly in the second series, when we differentiate m times and then put x is equals to 0, we get m factorial bm. That is from both the results, mth derivative of f at x is equals to 0 will be m factorial am and m factorial bm. So the derivative have a unique value, and equating m factorial am is equals to m factorial bm. From here we get am is equals to bm for all m. This is the uniqueness theorem. That is, if two power series converge to a unique function, to a same function, then the power series will be same. If the constant a and bn are equal, then both the power series are obviously also equal. Thank you.